If you come to the conference in person, you don't know who you're going to bump into in the hallway. You don't know exactly who you're going to run into at dinner, who you're going to end up sitting across from at the lunch table, but they could be your future collaborator, your future colleague.
Hey everybody, make yourself comfortable. Thank you for choosing my talk, despite how much good talks go in parallel. My name is Ruslan. My last name doesn't matter, don't care about it. So, I am a C++ committee member, but since I'm new here, let me introduce myself first. I'm working for Intel. I am oneAPI data parallel C++ or oneDPL lead developer, which is basically our implementation of parallel algorithms at Intel. I have significant contributions to other threading engines, including like oneAPI threading building blocks, so oneTBB or TBB, if you are familiar with that. I'm also a contributor to CppCon, which is yet another language for heterogeneous computing, like CUDA or from NVIDIA or HIP from AMD, but it was in the past. I am a contributor to C++ features within the standard, like std-cmd, std execution, and more. Of course, parallel algorithms, the thing that we're going to talk about today. Also recently, more or less recently, I stepped in a role of SG1 concurrency and parallelism co-chair in C++ committee. But that's my working part. I'm a pretty good singer. I'm a pretty bad guitar player. 16 months ago, I have a new hobby. I'm a father. Thank you. And I am a mountain biker. Don't worry, I landed. That's why I'm here. But that's a talk not about me, unfortunately. This is the talk about parallel range algorithms. So let's dig into that. So we probably mostly going to talk about like standardization and design. I'll show some implementations, but it's more about like motivation and the story, how we make this maybe happen. Spoiler alert, we will see. So let's talk first what are parallel algorithms. This is the algorithms that you probably get used to already, like AnyOf or for each or transform, whatever, with the execution policy as the first sample parameter. Instead namespace, taking iterators. Also, like you can see the example, like with findIf, we have begin and end for some input and some predicate. It's a serial version. The parallel version is exactly the same. You just put execution policy as the first parameter. Here's execution par, which means like do your best to execute it in parallel. What are parallel range algorithms? It's a P3179 proposal. So it's algorithms. Those are algorithms with the first template parameter constrained by execution policy exposition only concept. We will see it in this talk. In ranges namespace and taking ranges as one overload and iterator and sentinels as a second overload, like for like vast majority of them. Here's the example. We have std ranges findIf with some input, some predicate, and again the same. We do in this parallel. It's input and like predicate, and we add execution policy par being like one of the first parameter. And that's it. That's basically the whole talk. Thank you for attention. There is no much to talk about more. We're done. Of course, I'm kidding. This is the evolution, as I said, as I mentioned in my name of the talk. And we will see how we evolved it compared to what we have in C++ 17 for our algorithms. Just a disclaimer, we parallelize only the loop, so basically findIf. We don't pass the execution policy to any of ranges. We didn't modify, we didn't propose to modify any views or ranges in the standard. We're talking about only algorithms. The motivation. Partially, the motivation was was covered today for somebody who participated in your talk. Like, what's your name again? Like
Daniel.
Daniel, yeah. In Daniel's talk, we have some small intersection, but as I said, like very small in my opinion. But the idea, the motivation is pretty similar. So we combine the powerfulness of ranges API with parallelism. This is opportunity to fuse parallel algorithm invocations into one. It's better expressiveness and productivity of the code, and this is the ease of use. That was our motivation to write a proposal. Let's look at the example. We have state transform, state reverse, and state find if. Like, those take some inputs, take, of course, execution policy as the first parameter. But what is actually we can say about this code? We have 3 algorithm invocation, and each invocation adds its own overhead, meaning that we need to wait until the previous, like, invocation completes, for example, transform completes, until we can start reverse, and so on. And the unnecessary work might be skipped only for the last algorithm. By unnecessary work here, for find if, I mean that if you already found some element in memory, like in some position, you can basically skip searching all the elements from the right of this element, like in memory, because like the find if by semantics returns you the leftmost found. Looking at this example, you can say that this is a little bit artificial because honestly, we could, instead of doing transform and reverse, instead of reverse, we could do like find last if, or whatever it's called, something similar to that. And then instead of transform, we could basically use this lambda, which does +1 in this find if. But there is a very specific reason why this example is written like that. And the reason is here. This is because we have like these fancy iterators, and like spoiler alert, we have the same views to just show you how we transform this code to something that is lazy or pipelined, if you want, and computes on the flight. Of course, it has some differences. We previously did transform, so it also has some side effects on memory. Here, it's not the case. Like the iterators are lazy. And like, yeah, all the computations happen on the dereference. We used to make reverse iterator. We use DPL make transform iterator. We don't have transform iterator like fancy iterator in the standard. We need to use some third party. oneDPL is not the only library that provides that facility. The idea is pretty obvious. So what's the problem with this code? Before going to problems, it's one algorithm invocation, less overhead for parallelism. The unnecessary work might be skipped for everything, like it's just one algorithm call. But it's unnecessarily verbose, like it's a lot of verbosity. And as you can see, you should keep in mind that here, I hope you guys can see like my cursor. So we pass, even like to make reverse work correctly, we pass and as the begin to transform iterator of reverse iterator. If you wrap around your mind about that, it's like logical, but you need to remember about it, and this code like is not intuitive. Furthermore, it doesn't compile. Can somebody tell me why? Very quickly? Yeah, Andre, thank you. Andre says it's a lambda type. So despite the lambdas are spelled exactly the same, the type are going to be different. And of course, it makes our transform iterators type different, which does our reverse type iterators different. There is no type erasure. And our old fashioned algorithms require the iterator types to be the same. There is a fix. Of course, there is a fix. We just move lambda one line above on the stack and just use it. This code works. All other downsides are still there. So now we're going to use our powerful of ranges, but with old algorithms. Can we do this? Yes, we can. Thanks for the proposal that I think came from David Olson from NVIDIA. We can do this. Does it work? Yes, in principle it works. It does exactly what you expect. So data pipeline with transform, pipeline with reverse. It does exactly the same let's say, transformation going through the pipeline, as we did previously with our calls. We call findIf, it works. Again, the same goals are achieved, like one algorithm invocation, then as the reward might be skipped. It's still unnecessarily verbose. I mean, not that much, but verbose. And also, if you want to leverage the advantage of ranges having the iterator and sentinel be not the same type, this is not going to work. To be honest, I don't know any random access range where the iterator and sentinel would be different types. But who knows what awaits us in the future? What happens with our proposal? We have basically call-ins that ranges findIf with execution policy and the same pipeline. Everything's cool, right? I'm not going to repeat all the previous advantages, but it's also concise. And of course, it can work with different iterators and sentinels if it's the case in your code. There is again a problem. Can somebody tell me which one? This is Mark?
I can tell you which one.
Yeah, you know that.
Yeah, it's not trivially copyable, even though the lambda is.
No, this is not the problem I'm talking about. I mean, okay. And for this example, it's trivially copyable. It is. We don't have capture. Come to my lightning talk. Okay. We will cover what Mark is talking about. Okay. No, not this problem. Our res is unusable. This is the hint. Can somebody tell me why?
It's not borrowed range.
Exactly. Thank you. This is not borrowed range. Basically, when you pass Rvalue range and it's not borrowed, the result, the returning type is going to be std ranges dangling and not the iterator that you're able to use. That's unfortunate because I really think that std transform view could be borrowed. This is not the case, what we have in the standard. I hope, there is a paper that tries to fix it. I hope it will. But this is what we have today. So we need to fix it. We need to extract the pipeline to make it Rvalue, store it, use it, and now we have everything we wanted to achieve. Cool? I think it's cool. Okay. Bonus. We can use projections if you need. So, since it's an evolution, we should have some difference, right? Let's talk about them. Those are different, like some of them apply to the C++17 parallel algorithm, some of them apply to serial range algorithm, some of them apply to both. The execution policy as the first parameter is the obvious one. And yeah, we're just gonna go through them briefly because we're gonna talk more about them in details a little bit later. So we require parallel algorithms to have random access iterator and range. This is not the case for C++17. There it was like forward iterator. We require parallel algorithms to take sized ranges. We do need that for parallelism. Can somebody quickly provide me an example of random access range which is not sized?
Infinite iota.
It's,
and
yes.
Unbounded iota.
Yeah. Another example, that's a good one. Thank you, Daniel. Another one is like a C-string. It's a char, but you don't know the end until you find actually the null-terminated symbol. And this is probably the biggest change. We require parallel algorithms take range, not the iterator, as an output for the overload with ranges, and additionally take the output sentinel for the iterators and sentinel overloads. Let me show you what that means in our signatures. So here you can see serial signatures for iterator and range. We add execution policy template parameter, we add execution policy function parameter, and then we use this concept exposition only execution policy here, which does exactly what C++17 do, but just in concept syntax to be able to use it in constraints and simplify the wording of our C++ standard library. Then we say, hey, now everything is random access for the input. We don't touch output yet, both for iterator and sentinel and for range. Now we said everything is not only random access, but also sized. And we introduced sized random access range concept that is again not user visible. I mean, it's exposition only in the standard, just again to simplify the wording. And we made range as an output. So let's look at ranges overload. So basically we said that here, instead of taking like the O as the iterator, I mean, here strictly speaking, it's weakly incrementable, but let's just pretend for the purpose of this talk, it's like some iterator. We take it as a range. And again, size at random access range. So everything is range and everything is like size at random access. And for the sentinel overload, we basically did what I just described a moment ago. We just added the sentinel for the output and also make it sized. So I'm gonna switch to this slide. This is sort of side by side or top to bottom, whatever you like. Difference between serial range algorithms with iterator and sentinel overload, and the same for parallel one. So you can see all the differences are highlighted. Execution policy, random access iterator, signed the sentinel 4. Again, random access iterator instead of like weakly incrementable, and again, sized sentinel 4, and two extra parameters. For ranges overload, we have execution policy like size random access ranges for both input and output. Some tricks to get iterators out of ranges, and again, like one extra parameter and range instead of iterator. Are we good so far? Any quick questions? I want to keep big questions till the end, but quick questions I can take while we go. Okay, I assume we're good. So let's talk specifically about design, why we made this choice. First of all, let's talk about size random access range. As I mentioned, in the past we required forward iterator. But in practice, Intel, oneDPL, NVIDIA Thrust, GNU Libsted C++, and as far as I'm aware, who correct me if I'm wrong, lib C++ also goes with random access iterators for now. It's not done as far as I'm aware yet, but the choice is to go with the random access iterator. So this is the reality. This is the practical implementation that I'm aware of. My investigation showed the only Microsoft STL supports forward iterators. I mean, it's not, of course, the not performant one, but they support it. Again, this is the disclaimer, that's my investigation. There might be some other implementations that do this, I'm just not aware. And honestly, I had a very interesting conversation with Daisy Holman, and this was C++17 algorithm was standardized when I wasn't the part of C++ committee. And I asked her, like, why it like forward? And she said, you know, if I remember that correctly, it was input till almost like the very end. Daniel is laughing. Thank you, Daniel. And somebody said, like, why it is input? And everybody in the committee just was like, yeah, why it is input? Let's just make it forward. This should be enough. Good design approach, right? And honestly, I think this story is true. I'm not sure how truthful it is. Like, I trust Daisy, of course, but I mean, like, there are stories here and there. I did my investigation in the Parallelism TS scan algorithms. Like this was before it was standardized. Actually had input iterators, so I kind of believe in this story. Random access iterator is a must for efficient parallelization for now. This is the best abstraction that we have in the standard, again, for now. Yes, we eliminate some potentially useful use cases like filter view, but maybe relax in the future. Don't get me wrong. I really like what Daniel said today. We're not going to relax it to bidirectional iterator. No. this is not the relaxation. We need some middle ground, but the what was in Daniel talk, like I don't think that the middle ground that Daniel invented in his library immediately fits with this buffer like chunked ranges adapter, because it violates our view concept semantic requirements. But at least his talk helped me to think more about that. Maybe we can come with some solution, but unfortunately not today, and definitely not for C++26. That deadline has passed. And size is also necessary to be known in advance for parallelization. So first of all, it's memory safe. We're not going to do some like memory overrun. We can check everything. It's not undefined behavior anymore. We are going to return you, if you're familiar with range algorithms, or better to say algorithms in ranges namespace, they return the positions where they stop. Last for your input, for like many of them, and basically the place where they stop in output. And you can check all of it. If it's an error in your case, handle it. If it's not, fine. But the point is, again, like it will stop. Like all the algorithms will stop whenever they hit the end of any of the ranges. Like no matter if it's input or output. We will look at this a little bit more in details. And performance. If let's say you do copy, you provided your range, output range, which is less than size of which is less than the input, it will just go to and copy until the output is filled up. And this is basically what memcopy _s, like safe version of it, would do. Yeah, so this is the design aspect we had the most debate about. This is the ranges and output, and here I'm just listing the algorithms, for you to understand which they basically form the family of those. They belong to the same. Like we're mostly going to talk about copy, but also touch on initialized copy as well. Here are our arguments. It's ease of use. We don't need to use the ranges begin or dot begin, whatever. We can just pass a range. It's better memory safety. It's potentially better performance, is in the previous example that I told you, and also ability to detect an error. We covered that. The objection was it's more complicated switch between serial and parallel range algorithms. So it means that basically it's not just aiding the execution policy. Another objection was inconsistency with serial range algorithms. Okay, and unclear semantics. Let's talk about it. First of all, about harder switch. While this is true, again, this is an evolution, and this evolution is not happening for the first time. I want you to look here on the iterator 2 first 2. As you can see, there is no last 2. This is a binary transform. There is only last 1. That basically means that we need to assume that the second sequence and the output sequence is at least as big as the first input sequence. But that was the algorithm from stud. The algorithm from stud ranges does different story. They add the sentinel for the second sequence or range for the second sequence. So basically they already do this improvement. In my opinion, this is a huge improvement, and do the transformation until whatever of input ranges exhausted. We just went further and say, hey, why output cannot be a range as well? So output and consistency. Everybody agrees, right, that the C++ standard is consistent 100%, right? In every single way. We don't have any inconsistency in the current standard. Of course, this is not true. Copy has weakly incrementable or iterator as the output, while an initialized copy, which does more or less the same, has the range as the output. like for the second overload, and the like extra sentinel for the first overload. So I think there are reasons for that. They are out of scope of these talks. But still, this is the inconsistencies that we already have. And this is, moreover, a precedent. And unclear semantics, I don't really think that this argument applies. You might think otherwise. So basically, there was some thoughts that, you know, this code where we have like V1 and V2, and we just call copy, might appear that we're going to allocate for V2. Make it as big as V1 if it's like smaller, and it's smaller in this case, right? The size of V2 is 3. But no, I think we just need to do what our algorithms do today. We just go to like the smaller sequence, and it's absolutely consistent in that regard with everything that we have. There is no any contradictory. So, and also algorithms that with the same semantic, one algorithm with the same semantics is an initialized copy, right? It already does exactly what we propose for the new set of overloads. But actually not algorithms. It's also an initialized move, which you can say, yeah, it's pretty similar to an initialized copy, but also partial sort copy, which is completely different algorithm. It also takes range as an output. So with that, I think that those, like we were able to convince C++ committee that those concerns are not really concerns. Like the first one I think still stands. Yes, it's harder switch, but in principle, nothing prevents us to add the overloads for serial range algorithms, which also take range as an output in the future. When? This is a different question, but design-wise, I think nothing prevents us. If you're interested, P3490 is the proposal that covers range as an output in details. Because of that proposal, we were able to, like it's a separate complementary paper that was written, we were able to convince C++ committee that this is the right thing to do. Are we good so far? Any questions? Okay, no small questions. Let's talk about algorithms with output and gaps, how I call them. And we are going to talk about them taking copy-if as the example. So let's try to implement copy-if actually. It's a very interesting algorithm to parallelize. Partially Daniel already, if you participate in his talk, like partially he already covered it, but we are going to write an actual code. And as a disclaimer, my code is not going to be the most performant. This is not the purpose. This is just for demonstration purposes only. And basically, it's one possible implementation. It should be done more efficiently. It, in principle, can have some bugs. Though I ran it, it worked. But you know, some corner cases mightn't be handled. And you know, there might be some weird code somewhere. But remember the main purpose. The main purpose to fit the code on the slide. So here's the implementation that I saw in one framework, and the author of this framework just claimed how quick this implementation is. There is sort of a lot of code, but the main thing is it does for each. And it just goes by indices, the capture is like input and output, and if predicate is true, and writes to the output if the predicate is true. It's just basically for loop. Do we like this implementation? For somebody who knows what copy-if does? This is the hint. Basically, here is the input, here is the output, and here is the result. Anything wrong with the result for copy-if? Somebody? Everything is okay? Oh, then we can throw the half of my talk. No, of course, it's not. Like, copy-if is like gather algorithm. There shouldn't be these zeros. It should be like 1, 7, 5, 3, 7, 9, and then the rest. And the rest is not interesting. It should be like this. 4 is not appropriate implementation for that. So let's think how we can implement it. Like our predicate here basically tries to find, odd numbers. If it's odd number, it should be copied. So here's the input. What we can do in principle. We can calculate the predicate individually for every element, and we're going to have a mask, but not bool mask. It's like 1 or zeros mask. And we do it in parallel. Then we can scan it. And this basically, again, if you don't know what scan does, it's basically partial sums. So to just be absolutely clear, we start from 0 as some initial element. We do 0 plus 1, it's 1, 1 plus 1 is 2, 2 plus 0 is 2, 2 plus 1 is 3, 3 plus 1 is 4, and so on. So this is the scan, but also what's interesting, it gives us indices for the elements that need to be copied. So looking here, we have 9, for example, which is has true or 1 as the calculated mask, and it goes to 4th index. And then we just copied this element. Is it clear? Are we ready to go to some code to see how it might be done? Okay. So I allocate the vector and do transform with execution policy that came to me, range as the input, mask as the range again as the output. We already leverage the advantage of our API. We don't write mask.begin. We move predicate and move projection. And again, this code is not fully generic. I missed some forwards. I don't care about them for the purpose of this talk. But I specifically put move here to show that we don't need predicate and we don't need projection after we did the first stage of the algorithm. It's done after calculating the mask. So, and this maybe for somebody hard expression like double invoke, it basically means invoke projection for X and the result of the projection just invoke with predicate. So it's basically the invocation of the predicate, whether it's true or false. And we convert it to size T because I said we need numbers. We do exclusive scan. So we don't have any numeric range algorithms, even serial. That's why we have to use the old-fashioned one. But it's going to work because we know that mask is the vector, and vector has iterator and iterator. It doesn't have sentinel. Those are the same types. And you can see how verbose it is, with always begin and begin, instead of just using mask and scan result. We can use the advantage of our proposal. And our initial element is 0. And then we do for each with zip. So we basically zip input, mask, and scan result. And the code might look a little bit verbose, but actually the thing that we are doing here is simple. We just capture result. We structure bind or unpack this, the tuple that came to us to input, mask, and result. And if mask is 1, we just copy, knowing the index. By knowing index, the input that we need to copy. That's it. I'll give you a little bit of time and probably think about some questions. Yeah, go ahead.
It's not clear to me that zip will work, how it will work in parallel.
Yeah, so basically parallelizing scan is a very big story. It's a separate topic, but scan is parallelizable. Transform is basically as easy as parallelizing just 4. For each is again 4. The question was sorry, I didn't repeat it. The question was how could it work in parallel? And I'm not gonna tell you how to parallelize a scan. It's 1 hour, maybe, especially if efficiently. We also need to return our stop points, right? For the input, for this implementation, it's not even a question. We basically traversed all the input. We need to calculate how much elements we actually copied. And here, our previous computations can help. We can just take the last element in mask and scan and do plus. So 6 plus 1 gives us exactly the number of elements that we copied, because like here we have like, we know it's like 6 elements, each one forms the new groups. And if the last element should not be copied, it would be 1 0 here, so it would be 6. But since the last element should be copied, we just make like 6 plus 1, and it gives us exactly the necessary result. We do it like, we calculate it as copy elements, and we do it like ranges plus range size, and begin like plus copy elements. But again, we have range as an output, right? We did not implement anything when the range is not sufficient to have all the elements from input that need to be copied. And here is why there is a space here. It's like not occasional. Let's think about it more. So for this example, everything is fine. If we have the output that is 7, and we need to copy 7 elements, it's again fine. There is no UB here. It's allowed to have output less, but like we can still copy all the elements. The interesting case is this one. So if we have, let's say, 4 elements, but we need to copy 8, and we know that we stop at this, like at element number 5. Of course, this is not the question what to return for the output, because of course for the output we return AND, right? We just traversed all the output. Output is done. What to return for the input? Opinions. We actually have 2 options. Who thinks that we need to return this 8? Because that's the place where we stop. Raise your hand. Not much. What else can we return? If not that, like there is very few hands, like what else can we return? The hint is here, actually. What if we stop here at 5, but for all our elements that remain, there is no true predicate anymore? We would probably like to return AND, right? Because we basically traversed all the input. We don't want to falsely return this 8, pretending that there were more elements for which predicate returns true, but it's just your user's fault that they didn't provide like enough output, or not like fault, but the API call. So it's better to return the first element for which the predicate is true, but it doesn't fit like the size of the output. This is the goal that we will try to achieve. Then the next question, how we can achieve that? So there are 2 interesting properties of the scan of the mask. The first property is, as you can see, let's look at this group is like all 4s. Yes, it was formed after 5 when we added 3 to 1, we have 4, but again like 4, 4 plus 0, 4, 4 plus 0, 4, and then 4 plus 1, which is 5, and it forms again new group. But new group like for the, for the next elements. The point is, the number from each group that's going to be copied is always the last one. And also, this sequence is sorted. So we can use some binary search algorithms, which are, let's say here we are going to use upper bound. What I'm going to try to find with upper bound is the size of my output and see what upper bound returns to me. Because I really want to try to find the element which doesn't fit. And upper bound returns me the first number that is greater than the number that I requested. So for 4, as we have here as this output size, it's going to return 5. And since I want to try to find the last element, I'm going to do -1, like just pessimistically. And then I'm going to check whether my size was sufficient. And if it was sufficient, of course, I just, copied everything. The output size was sufficient. I copied everything. And if for this example, my last element, like my size is not sufficient, or like it's exact match basically. But my last element, which I have, like has the mask equal to 0, that I'm also gonna assume that it's the last one and the mask is 0. So then I'm also gonna assume that I copied everything. It's a little bit complicated stuff, but let's try to implement it. Again, this basically tells what I just said. We do upper bound, we do -1 pessimistically. We check if it's enough space here by just checking like if size is greater than scan back. And again, if it's enough space, I wouldn't need to do even like upper bound. But again, remember the main purpose. The main purpose is to feed the code on the slide. So after that, I'm checking what I just again said. Like I'm making +1 back. Like I did -1 pessimistically, and I do +1 back if the space was enough, or if this is the last element that I might need to copy, but I don't need to if the mask is 0. Then I do +1 and return basically to the end, like in this case. Then I need to calculate distance for that. And then use this distance to make zip smaller. The property of zip, it just goes to the smallest sequence within it. I calculate the distance, I use it to make zip smaller. I haven't changed anything in for each. And then I just calculate the number of copied elements based on this distance that I have, again, just by adding the scan value to the mask there. And here I'm also going to use distance. That's the number of elements that we traversed and the number of copied elements we just calculated. I'm going to pause here. I'm pretty sure that somebody is lost, but fortunately we have the recording on YouTube. You can rewatch it if you're interested in that. And again, this is sort of a bit complicated stuff. Any quick questions? I'm not hearing anything, but the good news is we are done with the hard stuff. Let's just continue enjoying the talk. So we have heterogeneity and performance here. I'm going to show the heterogeneous example based on oneDPL. As I mentioned at the beginning of my talk, those are the implementations of this is implementation of parallel algorithms, which was the former product which called like Parallelism, which we donated to LLVM and is currently used as GNU libstat C++ implementation. LLVM decided to go their own path. It supports heterogeneous execution via SQL, the language that I mentioned at the beginning of my talk. Currently the part of like Open Governed UXL Foundation. We have both specification and the code. And now we have implemented 35 algorithms as the product quality, and roughly 15 are coming in the next release. So I hope you're still alive and remember the example that we saw at the beginning with this transform, views reverse, like and data, pipeline, and find if. And let's see what does it take to basically execute it on GPU using SQL and oneDPL. First of all, we use SQL queue. I'm not going to talk about SQL almost at all, but just for your understanding, the queue there is the default way to submit the work. Just the thing that associated with some SQL device, heterogeneous device. Then we need the memory that is accessible on both CPU and GPU. We are going to use like unified shared memory allocator with the access to memory as shared, and we're going to construct this allocator with associating it with this queue. And then we're going to create the vector with this allocator to allocate some data that we need, of course, assuming that we fill this data. And we also use subrange. And we're going to work with subrange because we, for now, don't support vectors like being passed directly. This is a little bit unfortunate, but I hope we will be able to deal with this limitation. So that's the machinery before making the invocation, and to modify the invocation, the pipeline looks exactly the same. We don't change it. What we change, so we basically work with standard views. What we change is namespace for the call and create some of our custom execution policies, which is device policy, and again associating it with the same queue. That's basically it. That this code will run on GPU if your like default device for the SQL queue is GPU, or you can, SQL has the API to explicitly say with which device is going to be associated. Here's some performance measurements. So basically, this is the chart about the same pipeline. The baseline here is 3 algorithms call, so transform, reverse, and find if. Then we have 16 million of elements, and our target for find if is like roughly in the middle. Because if the target for find if is like the first element, there is no point to parallelize anything, right? It's just boom, done. And then we are showing the speed up here. So high is better, and we show the speed up against this like 3 algorithm call. The light blue one is the 3 algorithms call, but parallel ones with iterators. The dark blue is parallel range API call, again 3 of them, but parallel algorithms. And the yellow one is the pipeline, like basically the call with our proposal, 1 call with 3 pipeline algorithms. And as you can see, we have like 12x roughly speed up for the first 2 parallel iterator, parallel range like calls, like 3 algorithms, and 30% compared to the baseline, 30x compared to the baseline as the speed up for pipeline range. And the situation is even better on GPU, like roughly 78 and 75 for respectively for 3 parallel algorithms calls with iterators, and with 3 parallel range API calls. And with pipeline, we have 130x speed up. Of course, the even serial pipeline range call would be better than 3 because we don't have these effects on memory. So I draw the line like with 3.8. This is the speed up serial 3 calls versus serial 1 pipeline call, just to give you an idea how like the serial 1 would be faster even without any parallelization. So scope and status. Here we have a table, and of course I don't want you to like read it. The whole point of me showing this table is you should keep in mind that we standardized everything that was a part of C++ 17 algorithms, I mean parallel algorithms. We have the same set for ranges, except numeric. And I'm gonna talk in a minute why like without numeric. With the green color, we just showed, like, to give you an idea roughly, as let's say it's a map, like not the actual names. With the green color, I showed the algorithms that are implemented already as a part of oneDPL. With the yellow color, the algorithms that are coming. This slide basically talks that there are some only ranges only algorithms. There is no counterparts instead. Those are only instead ranges. And we look at those, and they are all based on the existing algorithms. So we were thinking, why not? And we just added them as well. and 3 of them are already implemented. Out of scope for this paper. So we didn't add anything new that was not the part of, except these 10 algorithms that I mentioned, but from the STID namespace, if there is no policy today for C++17 parallel algorithms, we don't add the execution policy for ranges algorithms as well. Because those are either not parallelizable, I mean, there is no point to do that. Like lower bound, upper bound, binary search, or it requires like a big exploration whether it's actually beneficial to parallelize them, and we didn't do that. We can always add them later if somebody thinks it makes sense. The use cases are also questionable from my perspective. So algorithms from numeric, like the reason is simple. We don't have numeric range algorithms at all, except IOTA. I mentioned that at the beginning of my talk, but I just want to explicitly repeat it one more time. There is no like state ranges reduce, state ranges transform. We just don't have them. I hope we are working together with Mark. Hey, Mark. To add them. But it's going to be C++29. And I hope we will be able to add both. I mean, both serial and parallel. We are not focusing on parallel only in our proposal, at least in the current stage. And there are 2 algorithms from ranges that are out of scope, which is fold and generate random. Generate random, it was a deliberate decision by Library Evolution to not include the execution policy. We can extend it if we see the value, but this is a very random number generator specific algorithm. And fold is just specified to be serial by nature. Like there is a specific order of iterations, so we cannot parallelize it. We need something like state ranges reduce. This is the proposal status. It's accepted for C++26. I hope it's going to be released. Nobody will have them concerns as our reviewing process and bug fix process. But I hope you will have it, and you could already try our oneDPL implementation and play with it. It's definitely better productivity and expressiveness in my opinion, and it gives you better performance if you have like use cases for that. And here is like further work. We have numeric range algorithms, as I mentioned. We have synchronous parallel algorithms with senders and receivers. We also have asynchronous parallel algorithms with senders, like based on senders, I guess. This is supposed to be our default asynchrony model. And our stretch goal is to add range as an output for serial range algorithm that I also mentioned. So this is sort of stretch goal because, focusing even on first 3 is already a ton of work. And I would like to give some special thanks to some people. Some of them are famous here, some of them are not. Alexey Kukanov is my co-author, so he put a lot of work in this paper as well. Not as much as I did, but yeah, I'm very thankful. It was easier to without him it would be harder, much harder. Jonathan Müller, basically for objecting. Yes, this is special thing for objecting. And he was objecting loud to range as an output, but it basically forced us to go and understand the problem better and convince him that this is the right thing to do. Inbal Levy, we were in Poland and we were about to see this proposal, but unfortunately it was moved out from the schedule. So we had a very big chance to not have this proposal for C++26, but she organized out of a cycle Telecon. We were able to review it and review it again in Hagenberg in Austria, like in February, if I'm not mistaken, and make it through Library Evolution. And then, thanks to Jeff Garland and Jonathan Wakely, who are chairs of Library Working Group, who decided to schedule it for telecons in between Austria and Bulgaria, which was like in June this summer. We already finished this proposal even before like coming to Bulgaria, and it was just a formal vote there. And Zach Lane and Jonathan Müller again for reviewing my abstract for C++ Now. This is not the title, not for CppCon, for C++ Now. Because that's the first time where I delivered this talk, and it probably wouldn't happen if not my first talk at C++ Now. The feedback though was the abstract looks good as is. So yeah, in C++ Now we have like 1 hour and 30 minutes as a regular talk. It's like more, extended version of this talk. But we also leave for each out of scope. We have a different return type there, but it's very easy to understand. And we also leave reverse copy and rotate copy out of scope. Those are very special algorithms. They also have different return types. And I would need like another 20 to 30 minutes explaining it to you why it's different and what design decisions we made. And I would completely overwhelm you with that, I'm pretty sure, because like I already feel that I overwhelmed you with like copy if example. So definitely out of scope for this talk. But if you're interested, here are some useful links to read about oneDPL, about SQL, about all our proposals, like the main one, the complementary two. That's what we have. I have some bonus. I will prioritize questions, if there are any. But my main part of my talk is done. I hope you enjoyed it. No questions? Everything is unclear? Sure.
Can I ask a question about your backend? Like what happened when I call it? Does it spawn lots of threads in your implementation? Or is there a thread pool and it's always...
Thread pool.
Right.
Thread pool. And actually we have different backends. We have the backend based on TBB. We have backend for oneAPI. It's not, the second one is not optimized though. For TBB, it just reuses TBB thread pool and doesn't spawn the thread. It's like task, work stealing based model.
Like how long does the thread pool live? I mean, like as long as the process...
The lifetime starts implicitly and it lives till application dies.
Okay, cool, thanks.
Anything else? Okay, so if somebody wants to chat with me like after this talk, I'm available, find me and let's chat. I'm not sure if, there are some available slots for lightning talk, but I'm gonna go and submit my bonus as the lightning talk. It's really short. So if it's accepted, you're welcome to see it there. If not, sorry about that. That's it. Thank you for attention and thank you for coming.